Can you see me? Okay. Okay, so what?
Floor is yours. Please start.
Okay, I'm Kennedy Sand, and I research the electron in an electric field. So when an electron is in an electric field, the electron experiences a force in a direction that is opposite of the electric field, and then it accelerates along the direction of the electric field. So I wanted to determine the rate of the electron transfer by observing the slopes. So my hypothesis is I believe the greater the electric field strength, the higher rate of electron transfer, and the slope will help us determine this by the amount of change between each electric field value. And at the end, you'll see that this also agrees with Ohm's law. So the methods I used for this simulation was a wave packet code in MATLAB to determine the results. So the code that I implemented, the principle of propagating quantum state of a model psi x of t forward in time to the future psi x t plus tau with an evolution operator of this equation, and with the evolution operator being that u hat of t, and then this is defined in the terms of the Hamiltonian operator of h hat with this equation that is given, and that is composed of kinetic energy parts and potential energy parts. So the potential energy operator includes two parts, which is a permanent part and a variable part. So the permanent part consists of the V times Vx, and this models the attraction of an electron to the ions of a semiconductor. So you see here the donor for X midpoint, acceptor for the X midpoint. And then the variable part mimics the exposure of the model to the external electric field. So this consists of V of X equals V times V of X minus and then the integral of ER times dr. So in this equation, the E is the electron and the EX is the electric field. And let's see, the overall potential yields a constant slope that is equal to the value of the electric field strength in the x direction. So then we simplified that equation above to just Vx equals V times Vx minus E to the sub x times x. And so the part of the code that I used to specify this information was V equals V times V minus X times, and in this case I put 0.1. So that 0.1 is considered to be the value of the electric field strength projection. So I used values that ranged from negative 0.05 volts to 0.05 volts, and I incremented them by 0.005 volts to get a total of 20 runs of the quantum state evolution in MATLAB. And so the initial condition, just to note, the initial condition for the wave function was chosen as the Gaussian distribution, which is that equation right there. And then we needed to convert this wave function into an observable for analysis and comparison. So the imaginary wave function was then converted into probability distribution by this P of X of t. So the donor semiconductor is the P sub D of t, which the equation is given there. And then the acceptor semiconductor was P sub A of t, and then that also is given there, the equation. And the difference between the two are just the integrals. So the integral of the donor semiconductor went from X minimum to X midpoint, and the P sub A integral went from X midpoint to X maximum. And then we'll note here that if you add the donor semiconductor with the acceptor semiconductor, it will be equal to 1. And then to convert this into a MATLAB code, we use the variables AVE-PL3 for P sub dt and AVE-PR3 for P sub A of t. And then methods continued. So for kinetics of the energy, kinetics of the electron field driven transition has a single exponential dependence of this P sub A of T equaling to this equation. So then if we solve for K in this equation, we'll get the reaction rate constant, which is equal to that equation, the K equals, and then we implemented that equation in MATLAB to get this K3 equation with the variables of infinity equaling n tau, dt equaling tau, and then that integral equaling the sum of AVPL3 times tau. So then this K3 value that we get, this value allows us to use an alternative way of finding the electron transfer rate. So after every run I did, I got a new K3 value. And so then here are my results. So in figure 1, let's see here. Sorry. So figure 1 shows a graph with the electric field of being 0.01. Figure 2 shows a graph of the electric field being negative 0.01, and figure 3 shows a graph with an electric field of negative 0.005, and figure 4, it's supposed to be 4, sorry, shows a graph with an electric field of positive 0.005. So as you can see from these graphs, figures 4 and figure 1, they're both positive electric field values, and they look pretty similar to one another with the green lines, as they both have a positive slope, and the green line in figure 1 rises more than the green line in figure 4, which is to be expected when comparing an electric field of 0.01 to 0.005. And we'll also notice that figure 2 and figure 3, so the figure right under figure 1, there are similarities in the green line as well, due to the fact that both of the electric field values are negative. But again, figure 2 decreases at a faster rate than figure 3, which is also to be expected when we're comparing the values of 0.01 to 0.005, just negative. So as a recap, when you have a positive electric field, you generate a positive slope, and a negative slope generates a negative electric field generates a negative slope. So a greater electric field value results in a greater increase or decrease, and a smaller electric field value results in a more subtle increase or decrease. And so here are more graphs. So figure 5 is the result of the electric field value that has a value of 0.05, and figure 6 is the result of the electric field value that has a value of negative 0.05. So these lines represent the probability of finding the electron at the left or the right side of the simulation cell. So the lines that are starting at 1 represent the probability of finding the electron on the left, and then the lines that are starting at value 0 represent the probability of finding the electron on the right. So as the wave function distributes from the left to the right, we get the graphs that are pictured here. And from this, we can determine what the slopes of these values are of the electric field, and we find the slope by calculating the probability over time. So in this case, it's just the y over the x value. And we use this slope to help determine the rate of the electron transfer, with a greater change in slope resulting in a higher electron transfer rate, and a slight change in slope resulting in a low electron transfer rate. So then here is the graph of the electric field versus the slope. So what we can see from this figure is, towards the left, we have our negative electric field values, and we can see that there wasn't a big change in the slopes, which tells me that there's a low electron transfer rate during those values. And then when we move toward the more positive values of the electric field, we notice there is a greater difference in slopes, so there's a higher rate of electron transfer at those electric field values. And my conclusion is my hypothesis of the greater the electric field strength results in a higher rate of electron transfer stands to be true. Based on my electric field versus slope graph, we notice that the slope helped us determine the rate of the electron transfer with the electric field strength. by noticing the greater differences in the slope values, resulting in a higher rate of electron transfer, and where the electric field strength doesn't change the slope as much, results in a lower rate of electron transfer. And that is all.
Okay, please join me in thanking Kennedi.